Yeah.
Anything that they just you just have to ask me before I start the lecture. Nothing.
Uh, no. Well, the web assigned where it has the chapter 8.8, but I think we went over that, right?
No, that's a Janessa. That's a really good question to ask. If you look in your calendar, that is a section that's actually out of the intermediate algebra book. In our
Okay.
course, a couple the way I'm going to run the class, most of the class comes out of the elementary algebra book, but on Wednesday of this week, I'll be doing section 8.8. But if you look at the calendar, it says that's from the intermediate text. Now, the intermediate, that's an OpenStax textbook also that's freely downloadable. So you don't have to purchase anything. You don't have to do anything with WebAssign or anything like that. That's already taken care of. So don't worry about any of that. But that's out of the section 8.8 from the intermediate algebra book. Okay.
Okay. Cool. Thank you.
Uh-huh. No, and I definitely need to mention that again. I should have actually, when I sent y'all the weekly update, I should have pointed that out. But yeah, section 8.8, and so pay attention to your calendar because there's going to be other sections um, during the last part of this class where we're going to use the intermediate textbook. Not immediately, but section 8.8 out of the intermediate book is the first one we're going to look at. But then later in the semester, we'll look at a couple of other sections that are out of the intermediate algebra book. So, all right. So I guess outside of that question, which was a good question, no other questions. So then we're going to go ahead and get started with higher order roots and talk about what that means, and then we'll look at fractional exponents and et cetera, et cetera. So higher order roots. So far, what we've been talking about is we've been talking about square roots. And so, for example, when we write the square root of 36 with a radical symbol like that, that is actually a shorthand for that symbol right there, where there's a little 2 written there inside the radical, and that 2 is called the index of the radical. And that index is usually just not written if it's a 2, right? The index is not written if it is a 2. And then what does that 2 tell you? That 2 tells you that when you're talking about the square root of 36, you're looking for a number that when you square it, you get 36, right? And the positive number that when you square it, you get 36. So since 6 squared is equal to 36, then the square root of 36 was equal to 6. No big deal. Well, that root can be, or that index can be any whole number. It's also the root. We write index there, but it's also the root. So it could be a 3, for example. And if the index is a 3, now you're talking about a cube root. And if you've got a cube root, then just like with square roots, in the same way with square roots, you're looking for a number that when you cube it, you get 8 is the answer. Just like with square roots, you're looking for a number that when you square it, you get that number. So here we're looking for a number that when we cube it, we get 8. And so that number is 2, and so we say that the cube root of 8 is equal to 2. Right? And the 3 in this case is the index for that radical, and that's the root that we're talking about. Right? If you have the 4th root, let's say we have the 4th root of 625. Generally speaking, I'm not going to be talking about numbers like on the test that big, certainly. And this would be called a 4th root. And so in this case, the index here is 4. That's our index. That would be the root that we're talking about in the problem. And so we're looking for a number that when you raise it to the fourth power, when you raise it to the fourth power, that you get 625, and that would be 5. 5 times 5 is 25, times 5 is 125, times 5 is 625. So the fourth root of 625 is 5. If we had, we could go on like this, certainly. So the fifth root of 32, right, that's our index, is 5 in this case, and this is called a fifth root. And so we're looking for a number that when you raise it to the fifth power, right, what number raised to the fifth power gives you 32? And the answer to that is 2. And so the fifth root of 32 is equal to 2. All right? And so that's what we're talking about with roots, higher order roots. And we'll talk about third roots, fourth roots, and fifth roots in this section. All right, now, as far as the ones that you should know, so like let's make a little chart here, sort of, or a table. These are numbers you should know on sight. So with square roots, you should certainly know that the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, and so on. These are ones with square roots that you should know from on sight, definitely. And a pretty lengthy list for square roots. You should know really up through 13, in my opinion, would be okay. You at least knew up through 13. And actually, if you went up to 14 and 15, that would even be better. Right, so those are perfect squares, and those are the roots for square roots that you should know. Cube roots, that list is smaller. So the cube root of 1 is 1. Cube root of 8 is 2. Cube root of 27 is 3. Cube root of 64 is 4. Cube root of 125 is 5. If you at the very least know up through that one, that would be good. If you knew the cube root of 216 was 6, that would even be better. And so that would be the perfect cubes. The perfect fourth roots, certainly the fourth root of 1 is 1. The fourth root of 16 is 2. Fourth root of 81 is 3. And if you knew up through that, that would be fine. And then the fifth root, if you at least knew that the fifth root, the fifth root of 1 is 1. And the fifth root of 32 is 2, if you at least knew those. So these are roots that you should know. Roots you should know on sight. So in other words, when you see these roots, you know that they're perfect roots. And then you can write down the value immediately, like that. All right. And my guess is most of you know most of those anyway, even if you really never thought about it or wrote them out like that, then most of you could recognize those okay. So that this shouldn't be too big a deal. Also, let's talk about roots of negative numbers for a minute. So we've talked about the fact that the square root of 4, for example, is 2, that it's not 2 and negative 2, but it's just 2, right? That square roots are defined to be positive square roots, or sometimes called the principal square roots. There's two numbers that you square to get 4, right? 2 and negative 2. But when you write a radical like that, and you write square root of 4, then you only mean the principal square root, or the positive one. And we've also talked now about the fact that the square root of negative 4, that there's no real number that you can square to get negative 4. And so we've just been writing that the square root of negative 4 is not a real number, right? So we write not real there. Well, with cube roots, notice, if you had the cube root of 8, you get 2. And notice there's only one real number you can cube to get 8. Unlike 4, right, where there's 2 numbers you can square to get 4. With 8, there's only one number you can cube to get 8. One real number that you can cube to get 8. Also notice that the cube root of negative 8, now that one it is a real number because there is a number you can cube to get negative 8, and that's negative 2, right? Negative 2 cubed is negative 8, right? With squares, there's no real number you can square to get negative 4, but with cubes, there certainly is. And so notice this kind of divides up even and odd as far as the way this works. That the even roots are ones that all are like the square roots, right? So we know that that the fourth root of 16 is 2, right? Even though there's 2 numbers you can raise to the 4th power to get 16, it's the positive one that we use when we write a radical symbol or use a radical symbol like that. And the 4th root of negative 16 is not real, right? That there's no real number you can raise to the 4th power and get negative 16 at all. And so notice square roots. Go ahead, Michelle.
Is the only time you're going to be able to have a real number is when the numbers are even? Like when the index is odd, I'm sorry.
Yeah, so when we have, so we're going to divide it up like this. Let me write one more down here real quick, and then we're going to kind of summarize it. So the 5th root of 32 is 2, and the 5th root of negative 32 is negative 2, right? So when you have even roots, right, the square root of a positive number is going to be a positive number, right? You're going to get a positive answer. And the square root of a negative number is not real. And when I said square root, actually, I'm going to put the nth root down for both of these. And so even roots so the index n is even, is what we're talking about here. So, you've got the square roots, 4th roots, 6th roots, things like that. Square roots, 4th roots, 6th roots. Those all fit in that category. So you take the square root of a positive number, you get a positive number. You take the 4th root of a positive number, you get a positive number. You take the 6th root of a positive number, you get a positive number. You take the 4th root of a negative number, it's not real. Take the 6th root of a negative number, not real. Right? Odd roots, right? So now the index n is odd. And what do we have? That the nth root of a positive number will be positive, and the nth root of a negative number will be a negative real number. Will be negative. It'll be a real number, right? And so this category are the odd roots. So this is the cube roots, 5th roots, 7th roots, things like that. Okay, so Michelle and everybody else, I don't know if that answered your question or not, but that's the way we divide this up, right? So so when you've got a negative number underneath the radical, when's the only time you get a real answer? And that's when you have an odd root, a 3rd root, a 5th root, a 7th root, things like that. If you have an even root of a negative number, then it's right now you're just going to write that it's not a real number. Okay. Does anybody have a question about that? Is that kind of clear to everybody, hopefully? So these are even roots here. These are odd roots here. Square roots, 4th roots, 6th roots is what we're talking about. In that category, this category, we're talking about 3rd roots, 5th roots, 7th roots, like that. Okay? Everybody's okay? All right. So let's see. So now let's talk about variables underneath the radical. Variables underneath the radical, and look at how that works. So roots of powers is what we're talking about here. Roots of power. So we've already talked about this with square roots a little bit, right? So we've seen that the square root of x squared, as long as x is a positive number, that the square root of x squared was equal to x. And the square root of x to the fourth power was equal to x squared. And the square root of x to the sixth power was x cubed. And so what do we see in these kinds of problems? That we knew the square roots of even powers, and what did you have to do? You just divided, in each case, divide the power by 2. Divide the power by 2 to get the root. Right, so the square root of x to the square root of x to the 32nd power would be equal to x to the 16th power, right? Because what number? And again, this isn't some magical rule here. Remember, the reason why this works like this is because you're looking for a number that you can square to get x to the 32nd power, because that's what we're talking about, is a square root. And so what power fits in there is x to the 16th, because you multiply exponents like that. So you divided the power by 2 to get the root for square roots. So now with cube roots, and by the way, if the kind of go back over this again, if the power was not even, so like an odd power like this one, then remember what we did is we broke it up into an even power and an x, and you got the square root of x squared times x, and that was x times the square root of x. And the square root of x to the 5th, we'd have broken that one up as the square root of x to the 4th times the square root of x, and that'd give you x squared times the square root of x. Square root of x to the 7th, we'd break that up as the square root of x to the 6th times the square root of x, and that'd give us x cubed times the square root of x, right? And that's how we would simplify those. All right, so this was all with square roots. So now let's do the same kind of thing with cube roots and powers like this. So we'll start off with the cube root of x cubed. The cube root of x cubed, we're looking for a number that when you cube it, you get x cubed as the answer, and so that would be x. So the cube root of x cubed is equal to x. So that kind of makes sense. That the cube roots and powers of 3 kind of undo each other is one way to look at it. And so then the next one we know is the cube root of x to the 6th. The cube root of x to the 6th, you're looking for a number that when you cube it, you get x to the 6th, and that would be x squared. And so the cube root of x to the 6th is equal to x squared. And you start seeing the way this pattern is going to work here. That you've got the cube root of x cubed is equal to x. The cube root of x to the 6th is equal to x squared. The cube root of x to the 9th would be x cubed. The cube root of x to the 12th would be x to the 4th power. So what are you doing with cube roots? You're dividing the power, in this case, by 3 to get the root, to get the cube root in this case. Right, so just like square roots, you divided the powers by 2. Cube roots, you divide the powers by 3. Now notice I didn't put the restriction that x had to be greater than or equal to 0 on the cube roots, because it doesn't matter whether you have a negative or a positive. These are all still the same rule here for cube roots. So then, and by the way, we're going to kind of summarize this again in a chart in a minute. So you have that the cube root of x cubed is x, and the cube root of x to the 6th is x squared, and cube root of x to the 9th is x to the 3rd, and the cube root of x to the 12th is x to the 4th, and so on there. Right? You divide the power by 3 to get the root. So if the power is not divisible by 3, so like let's say you have the cube root of x to the 4th, then you break this one up just like you do square roots. But you'd break it up as the cube root of x cubed times the cube root of x, and that would be x times the cube root of x, to simplify it like that. The cube root of x to the 5th, you still break it up as an x cubed. So you'd have the cube root of x cubed, but now you'd have 2 x's left over. So this would be times the cube root of x squared. And that'd be x times the cube root of x squared. The next one is the x to the 6th power. That one we know. So then we go on to x to the 7th power. Cube root of x to the 7th. We'd break that up as the cube root of x to the 6th times the cube root of x. There'd be one x left over. And so that'd give us x squared times the cube root of x. The cube root of x to the 8th. This would be the cube root of x to the 6th. That would be the biggest power that's divisible by 3. But there'd be 2 x's left over. And so you'd have x squared times the cube root of x squared. And you could just keep on going. And so the idea here is with cube roots is to pick the biggest power that's divisible by 3, right? That's what you're trying to do, is take the biggest power that's divisible by 3. Divisible by 3. So if you had the cube root of, the cube root of x to the 25th power, right? The biggest power that's divisible by 3 that we can get from x to the 25th would be x to the 24th. So you'd break this up as the cube root of x to the 24th times the cube root of x. And then the cube root of x to the 24th, you divide the power by 3, and you get x to the 8th. And then you'd have this cube root of x left over like this. All right, same thing with the same things we're talking about here with cube roots would extend to 4th roots and 5th roots. So what do we see? That the square root of x to the a, this is a square root. What do? We divide the power by 2. With cube roots of x to the a, we divide the power by 3. So with 4th roots for x to the a, we divide the power by 4. Fifth roots, we divide the power by 5, and so on. You know, so the 4th root of x to the 28th power, right? As long as x is positive because it's an even root. The 4th root of x to the 28th, what do? We divide the power by 4 in this case, and that would be x to the 7th. Right? That's all we're talking about doing here. Now, you know, I'm not going to go crazy with 4th roots and 5th roots and stuff like that. We'll do mostly cube root for higher order roots, mostly cube roots, 4th roots like that. So don't get too panicked here. All right, now simplifying.
Okay, I'm sorry, but I'm completely confused.
You'll be okay. Watch. So the square root, let's put them all together. The square root of x squared is x. The square root of x to the 4th is x squared. Watch it, and when I put them all right next to each other, Michelle. So with square roots, what are we doing? We're dividing the power by by 2 each time, right? With cube roots, what are we doing? We're dividing the power by 3. Like that, right? Every time we're trying to evaluate a radical like that, we divide the power by 3. With fourth roots, we divide the power by 4. So the fourth root of x to the fourth would be x. The fourth root of x to the 8th would be x squared. The fourth root of x to the 12th will be x cubed. Fourth root of x to the 16th would be x to the 4th, and so on. Fifth roots would be the same. What do? We divide the power by 5 in this case. And so this would be fifth root of x to the 5th would be x. Fifth root of x to the 10th would be x squared. Divide the power by 5. So what are you always doing? You're always dividing the power by whatever the index is to evaluate the radical. So that would be x to the third.
You have to break down the powers if it's not evenly divisible by the index.
Trina, that is absolutely perfectly said. You're exactly right. So if it's not exactly divisible, then you have to break it up. I could not have said it any better. So, for example, you have fourth roots over here. You're dividing by 4. So if you have a power that is not divisible by 4, right, like the x to the 18th, 18 is not divisible by 4. So what do we have to do with this one? Trina, exactly like you said, you're going to break it up. And what are you going to do? You're going to break it up into 2 fourth roots, and one of them has to be divisible by 4. And you want to pick the biggest one that's divisible by 4. So what's the power less than 18 that's the biggest one that's divisible by 4? What's the biggest power less than 18 that's divisible by 4? Anybody?
16.
Janessa or Trina, one of y'all I heard say 16. Maybe it was both of you, which is exactly right. And then how many x's are left over?
2.
Yeah, 2. And so there you go. You've got it split up. And then you just evaluate this one with the rule we've just talked about. That's x to the 4th. This one just comes down for the right.
Okay.
See, in this, if you know that pattern, this is going to extend no matter what the root is. So, you could do something crazy, like if this was the 8th root of x to the, let's see, the 8th root of x to the 32, first of all. What do? It's an 8th root, so you divide the power by the index. You divide the power by 8, and 32 is divisible by 8. You just get x to the 4th. No big deal. But if you had an 8th root where the power was not divisible by, not divisible by 4, like let's say we had the 8th root of x to the 45th power. Well, so 45 is not divisible by 8. And so what would you have to do to this one? You'd have to break it up into 2 8th roots. And what's the biggest root less than 45, or the biggest power less than 45 that's divisible by 8?
40.
40, yeah. And so this would be x to the 40th right here. And then how many x's are left over?
5.
5, that's right, good. And so what do you get then? You get the 8th root of x to the 40th. You divide the power by the index, and you get x to the 5th right there, 40 divided by 8. And then the other radical just comes down, just 8th root of x to the 5th. Okay, so it takes a little bit of practice, but hopefully Michelle, that straightens that out a little bit. The only other thing that you have to just be a little bit aware of here is that with even roots, you always have the restriction that the variable has to be positive. Odd roots, you don't need that restriction. So with odd roots, you never see that x has to be positive, but even roots, you're always going to have that it's positive to do this. All right, so now, so that's with we've concentrated on powers a little bit. So now let's look at constants and simplifying. So we've seen that the square root, for example, the square root of 20 was the square root of 4 times the square root of 5, right? We broke up the 20 into 4 and 5, and the reason why we pick 4 and 5 is that 4 is a perfect square. And remember, we need a perfect square to do this. So that's why we don't use 2 and 10 for 20, because 2 and 10, neither one of those is a perfect square. And then you get 2 square root of 5. And if you have a number that breaks up several different ways, like 48, right? 48 is 4 and 12, and it's also 3 and 16, but 16 and 3 is the one you want to use because 16 is bigger. So what do you need? You broke it up, and that was a perfect square right there. The 16, and so you got 4 times the square root of 3. Well, you have the same idea with cube roots. So, for example, the cube root of 16. Now, 16 is not a perfect cube, so we want to break up 16 if we can. It's not certainly not it's not that it always has to happen, but is there a way we can break this up into 2 factors where one of them is a perfect cube? So, in other words, is there notice not a perfect square in this case, but a perfect cube? Is there a factor of 16 that's a perfect cube?
8.
Yeah, 8. Good. Charlotte, so you have the cube root of 8 and the cube root of 2. That's how you break it up. And then the cube root of 8 is 2, and so you'd have 2 times the cube root of 2. If you had the cube root of, let's say, 54, right? 54 is not a perfect cube, but does 54 have a factor that is a perfect cube? Is there a fact? So, think about the numbers that you know are perfect cubes: 8, 27, 64. And so what would be a factor of 54 that is a perfect cube?
27.
27. There you go, Michelle. So you'd have 27 and 2. Right? And then what's the cube root of 27 is 3. And you have 3 times the cube root of 2. And notice the difference. Let me put this one right next to it. Notice this is the square root of 54, not the cube root of 54, but the square root of 54. And so notice that one is different. Square roots and cube roots are different. Now you're looking for a factor that's a perfect square. And that would be 9 and 6, wouldn't it? Right? Because 9 is a perfect square. And that would be 3 times the square root of 6. So, pay attention to the root and make sure that you know what root you're talking about. Now, as we get higher and higher roots, there's fewer and fewer of these kind that we're going to be simplifying because it gets harder and harder to identify the factors.
So is that answer different?
Yeah. What do you mean is the answer different?
Because that the square root is 6 on that one, the square root is 2 on the other one. So would that
No. Be careful what you just said, Michelle. This is 3 times the square root of 6. That's right. But the other one, the cube root, that was 3 times the cube root of 2. Right? Those are different roots. And so, yeah, definitely, remember what you're doing here is you've got 2 different numbers at the beginning. So you shouldn't get the same answer at the end because the numbers we started with at the beginning were different. Right? We had the cube root of 54 and the square root of 54. Right? Those are 2 different numbers. Right? Right? The cube root right? The square root of 54 is a number between 7 and 8, right? Square root of 54 is a number that when you square it, you get 54. 7 squared is 49. That's too small, right? 8 squared is 64. That's too big, right? So square root of 54 is a number between 7 and 8. The cube root of 54 is a number that when you cube it, you get 54, right? 3 cubed is 27. That's too small. 4 cubed is 64. That's too big. And so what do we get? That the cube root of 54 is a number between 3 and 4, right? They're definitely different numbers. We should come up with something that's different at the end also, definitely, right? So the cube root of 54, we break it up so that one of the factors is a perfect cube, and that's the cube root of 27. It's a perfect cube. The square root of 54, we break up so that you get a perfect square, right? That's a perfect square right there. Right, with square roots, you're looking for squares. For cube roots, you're looking for cubes. I don't know if I addressed your question or not, Michelle.
Yeah, you did.
Okay. And that's a really common mistake, by the way, is I'll put a cube root on the test and a student will treat it as a square root. So you have to really be careful about that. Like I said, the author tends to kind of go crazy with some of this, and they have you simplifying 6th roots and 7th roots and things like that. And we're just not going to be going crazy like that at all, just so you know. And the numbers are going to be not huge, so that you're kind of left to wonder what's going on with the factors and everything. So, going back to this chart that I had, where was it? Right here. Those are about as big a numbers as you're going to be dealing with any of the individual roots, just so you know. So as long as you can identify these roots on site, then for the most part you should be okay on the exam. Definitely don't expect the numbers to be just immensely huge or anything like that. I know you're not using a calculator, and so you're going to be okay. I'm going to keep it within reasonable ranges here. Now the other thing to just be careful about is if you've got the 5th root of negative 32, for example, well, that's an odd root. So since it's an odd root, the odd root of a negative number is okay, and that answer is going to be negative 2. But the 4th root of negative 16, right, that's an even root. And so what do you know automatically there? That if you have the even root of a negative number, that's not real. Right? And so you write not real right away. All right, so kind of pay attention to that as well. All right, so now what we're going to do, this is actually kind of extends, is an extension of what we've just done. We're going to look at exponents and talk about writing these things out with fractions as exponents. So as an example, let's talk about 4th roots for a minute. We've seen, so for example, we've seen that the 4th root of x to the 8th, what is our rule? Is that we divide the power by 4, and so you get x to the 2nd. Now what I didn't actually ever do there is I didn't actually write that out, that what you're doing is dividing the power by 4, so that's really x to the 8 over 4 power, and then that gives you x squared, like that. So, you could do that even if the power was not divisible by 4. So like you have the 4th root of x to the 5th, you could really write it as x to the 5 over 4 power. It's just that 5 is not divisible by 4. And so notice x to the 5/4 and the 4th root of x to the 5th then are the same thing, is what we're talking about. And this is going to be true really for any radical that has a power under it like that. That if you have the a root of x to the b power, just in general, that what you could do is you could write this as x to the b over a power, right? The only thing you have to be careful about is whether the index is even or odd, because that would control whether you can take the root of a negative number or not. But let's not get too hyped up about that yet. So what are we saying? That as an exponent, if the denominator is the root that you're talking about and the numerator is the power, and that's a way that I a lot of times like to talk about it, is that it's power over root when you're talking about a fraction as an exponent. So if you've got, and so by the way, let's go ahead and put a big box around this, that's kind of our rule for how you take a fraction as an exponent, how you rewrite it as a radical. So if we have, if we have x raised to the 2/5 power, then what is that? What's another way of writing that as a radical? With a radical, the index would be, or the root would be 5, and the power on the x would be 2. That this is the same thing as the 5th root of x to the 2nd power, right? Just using that rule that we've just written down right there. All right, and so notice that if you have just a square root, or you have a 1/2 power, let's just look at it that way first. If you have a 1/2 power, then what would the root be in this case? Well, the root would be 2, so we don't even write the index down, and the power would be 1. So this would be technically it'd be the square root of 2 to the 1st power. But how would we typically write that? We'd simply write that as the square root of 2. And so what do we have here? That the 2 to the 1/2 is the same thing as the square root. That when you raise something to the 1/2 power, you have the same thing as the square root of that number. By the way, it makes sense because we know that what happens when you take a square root and you square it. We talked about that last couple times in lecture. But when you take a square root and you square it, it's kind of like the square and the square root undo each other, right? When you take the square root of a number and square it, you just get the number that's underneath the radical. Well, look at what happens when you do 2 to the 1/2 power and you square that. The rule for exponents is that you multiply those exponents. So you technically have 1/2 times 2, and that's just 2 to the 1st power, or 2. So notice you get the same answer. And so if you get the same answer at the end, then it means that what you started with has got to be the same thing also. And so that leads you to this conclusion here, that the square root of 2 and 2 to the 1/2 power are really the same number. Because when you square them, you get 2 in both cases. So, so what would that mean then for us if you had, if you have 49 to the 1/2 power, 49 to the 1/2 power, then really means the square root of 49. You can write it as a radical, but that would be 7. So the 49 to the 1/2 power is equal to 7. 64 to the 1/2 power would be the square root of 64. That would be 8. If you want to write it as a radical, if you want it to help you keep it straight, you can always do that. You don't have to write that middle step out if you don't want to. You can just say that 64 to the 1/2, in your head you're saying, hey, I know that's a square root, and then just write the root down at the end. So 100 to the 1/2 power, what would that be? Shout it out, everybody. Anybody?
Square root of 10.
That's right, which would be So what would it be? Anybody? I heard somebody say that it would be the. I heard somebody say it would be the square root of 100, which is exactly right, and that would be equal to 10. Right, right. Let's see. 4 to the 1/2 power would be equal to 2. Yeah, because it's the square root of 4. That's right. So now, what if you have 1/3 powers? So if you had 8 to the 1/3 power, now what's the root? If you wanted to write this as a radical, what would the root be?
3.
3.
The root would be.
Yeah, the root would be 3, and so you'd have the cube root of 8 to the 1st power. That would be equal to 2. Right? 27 to the 1/3 power would be the cube root of 27. That would be 3. 64 to the 1/3 power then would be equal to 4, because that'd be the cube root of 64. Right? So then probably a good way to summarize that would be like this: that the square root of x is the same thing as x to the 1/2 power. The cube root of x is the same thing as x to the 1/3 power. The 4th root of x is the same thing as x to the 1/4 power, and so on. Right? The 5th root of x is x to the 1/5 power. Right? That's a good little summary right there, as far as these fractions where the numerator is a 1 and how they're equivalent to a root like this, that these exponents are really the same thing as roots in each case. All right. Now, I know this takes a little bit of getting used to. That's okay. It's going to take a little bit of practice, but as you practice these problems, you'll get used to how this is working out. So if we have, let's see. If we have 16 to the 1/2 power, right, we're talking about the square root of 16, right? And so that would be 4. Negative 16 to the 1/2 power, well, that's the square root, but it's the square root of a negative number, and so that would be not real, right? Because you've got the square root of a negative number. And again, you could write it out as a square root if you want to, as a radical, right? That negative 16 to the 1/2 power really means the square root of negative 16, right? That's not real, right? There's no real number you can square to get negative 16. If you're talking about cube roots, 27 to the 1/3 would be the cube root of 27, or be 3. If you had negative 27 to the 1/3, that's okay. That's an odd root, so not a problem there. That's going to be negative 3. Right? If you had, right, so remember, you kind of divide this up by even roots or odd roots as far as whether it's a real number or not a real number. With 4th roots, that's a even root. So 16 to the 1/4 power, that's the 4th root of 16. And if you need to think about it that way, that's fine. So you're talking about the number that you raise to the 4th power to get 16. That's 2. But negative 16 to the 1/4 power is not real, right? Because that's an even root of a negative number. So you remember, even roots of negative numbers, not going to work, right? Or at least it's not going to be a real number. With the fifth root, if you had 32 to the 1/5 power, that's the 5th root of 32. That's 2. No big deal. Well, I mean, it's a big deal, but it's 2 to the 5th power equals 32, so that's equal to 2. negative 32 to the 1/5 power, I can do that because that's an odd root. That's negative 2. Right? So even roots, what happens? Even roots you get of negative numbers, not real. Odd roots of negative numbers are negative numbers. All right, we definitely need something we definitely needed to talk about there. Also, don't forget all the other rules for exponents that come up that we've talked about before. They extend over to these fractions as exponents. So, for example, if you had, let's say we had 64 to the negative 1/2 power, remember that a negative exponent does what to a number? It flips it, right? It changes it into a fraction. So 64 to the negative 1/2 power is 1 over 64 to the positive 1/2 power. Just like x to the negative 2 is 1 over x to the positive 2, right? It's been a little while since we've talked about that in class, but that rule still extends over to fractions as exponents. And then 64 to the 1/2 power, well, that's the square root of 64, and so that would be 8, and so that's 1 over 8. Let's say we had 64 to the negative 1/3 power. 64 to the negative 1/3 power. So that would be 1 over 64 to the positive 1/3 power. Right? And so then that's the cube root of 64. And so that would be 4. So that's 1 over 4. All right. If we have just something like this, x to the negative 3/4 power, then to get rid of the negative exponent, right, we would just rewrite this as a fraction. This would be 1 over x to the positive 3/4 power. Right, just using the rules for negative exponents that we've seen before. If you have x to the negative 2/3 power over, let's say, y to the negative 1/2 power. Well, we've seen that kind of problem before. I'm going to kind of title these all examples here. Right, we have a negative exponent in the numerator and a negative exponent in the denominator. So what happens when you have negative exponents in fractions like that? It takes the factor and it moves it to the other part of the fraction. Right, so the y to the negative 1/2 goes to the numerator as y to the positive 1/2, and the x to the negative 2/3 goes to the denominator as x to the positive 2/3. Right, you just get rid of the negative exponents the same way we've done before with other kinds of problems. Right, it just moves it to the other part, moves the factor to the other part of the fraction. All right. Do you remember the rule? What do I do with exponents like that? If I had, and no fractions as exponents in that problem, but just to go back and review for a second, what do you do with those exponents?
You just add the exponent.
You add them. So that's right. Very good. So that's x to the 5th. So you do the same thing if you have fractions as exponents. You add those just the same way, same rule, right? So this is the same rule. But what's the issue here? The issue is when I add these exponents, what do I have to do? I mean, what's the issue there?
Change the denominator to the same.
Very good, Trina. That's right. You need the denominators to be the same because they're fractions. And so to add them together, you got to have a common denominator. So you end up, the common denominator there is 6. So you have 4/6 plus 3/6, right? 2/3 is 4/6 and 1/2 is 3/6. And so you end up with x to the 7/6 at the end, like that. You just add the exponents, right? So that rule is exactly the same as what you've seen in the past. But it's complicated because it's complicated by the fact that you need to get a common denominator on the exponents. All right. What's the rule we use in this problem for exponents? When if I have x to the 5th raised to the 3rd power, what's the rule there?
Multiply the exponents.
Multiply the exponents. That's right. Good, Trina. So that gives you x to the 15th, because that's just x to the 5 times 3. Well, that rule is exactly the same if you have fractions as exponents. No difference. So if I had x to the 2/5, and that was raised to the, let's say, 4/3 power. Now, I always give a problem very similar to this on a test. Always do. And this material will be on your exam too. So expect a problem that's very much like this one right here. It's the same rule, isn't it? Right? You multiply the exponents. So this is the same rule. And so this should be x to the 2/5 times 4/3 power, which would be, in this case, you just multiply the fractions, and there's nothing to cancel out there or anything, and you just get x to the 8/15, like that. And you know, if you know that that's the rule, that you multiply exponents when you have something raised to a power and then raised to a power again, this is a really simple problem. And you'd be surprised. I bet on the last time I taught intermediate algebra, I guess that was in the spring, I bet I had half the class miss this question, or miss a question that was similar to this one, because they added the exponents in this problem, or they did something crazy. I don't know. All right. So here you multiply the exponents. So multiply exponents. All right, so what's the rule in this case? So I have x to the 6th over x to the 4th. What do I do with those exponents?
You subtract them?
You subtract them, that's right. Very good. So you have x to the 6 minus 4x squared. Right, I subtract exponents in this case. And so if the exponents are fractions, the rule is exactly the same, right? There's no difference in the rule at all. So if I have x to the, let's say, 4/5 over x to the 1/4, then what do I do with those exponents? I've got to subtract them. The problem here is that this rule is kind of complicated by the fact that these are fractions as exponents, and so I've got to get a common denominator. The common denominator in this case would be 20, right? Yeah, so you have x to the 16/20 minus x, or no, I'm sorry. You'd have 16/20 minus 5/20.
That's my question. Okay, so you know how when we multiplied the exponents, we didn't worry about, the denominators being the same. But let's say, for example, what if we did make the denominators the same? Would the answer come out differently?
No, but you'd be making the problem so much more difficult. To do that. So there's no, since you don't have to find a common denominator to multiply two fractions, right? You'd be making the problem a lot more difficult. Let me show you what I'm talking about on the problem at the top.
Well, I get it. I was just making sure. So say, for example, if somebody did it on a test, or like that, it doesn't make them confused.
Well, they might get confused, but look, by the way, let me finish this problem. So this is x to the 11/20, by the way, right? To finish this problem up that we were just doing where you subtracted the exponents. By the way, let's review this one more time. As a radical, this last problem, if you were going to write it as a radical, remember, it's power over root. So x to the 11/20th power would be the 20th root of x to the 11th power. I just want you to be able to go back and forth between exponent form and radical form. And so I just wanted to say that one more time. Now, so look at this problem here, Michelle. If you had decided to get a common denominator when you multiplied those fractions, you're not changing the fractions, so you're right, you can do it, but watch how hard you make your life, because the common denominator there is 15, and so this is x to the 6/15 times x, and let's see, 4/3 would be 20/15, and then you'd multiply those fractions and you'd get x to the 120 over 225 power, because 6 times 20 is 120 and 15 times 15 is 225. And then what would you have to do? You'd have to reduce that, and you're going to get x to the 8/15 there, but, you know, that's not trivial to reduce that fraction at the end. They are the same, but you'd have to cancel some common factors out there at the end to get that. So it's kind of a pain to do. So you're just making your life so much harder by doing that when you don't need to, right? You're making the numbers a lot bigger by getting a common denominator there. But you can. There's no question you can do that if you wanted to. So, all right. So on your exam 2, I'm telling you right now, there are going to be 3 problems right next to each other that are going to look like this. You're going to have, let's say, x to the 1/3 times x to the 3/4. You're going to have x to the 1/3 raised to the 3/4, and then you're going to have x to the 1/3 over x to the 3/4. Because what do I want to know? I want to make sure that you know when you add, subtract, or multiply the exponents. And so notice you're going to have 3 problems like that. They're going to look like this. What are you going to do here? You're going to add the exponents. Here you're going to multiply the exponents. And here you're going to subtract the exponents. I want to make sure that you know when to do which one of those rules, right? And so those will be 3 problems right next to each other. I'm not saying that those are going to be the exponents, but it's going to be something like that, right? So this is going to be x to the 1/3 plus 3/4, right? Add the exponents, get a common denominator, which is 12, and so you'd have x to the 4/12 plus 9/12, x to the 13/12. On this one, you're going to multiply exponents. We're not going to get a common denominator there. We're just going to leave it like it is. And in fact, notice the 3's divide out. When you multiply those exponents, then you just end up with x to the 1/4. This one, you need to get a common denominator to when you subtract, because you have 1/3 minus 3/4. So it's similar to the very first problem, except it's subtraction. So this is x to the 4/12 minus 9/12. And so that would be x to the negative 5/12. And notice you would not leave it like that because it has a negative exponent. You'd get rid of the negative exponent at the end and write it as x 1 over x to the positive 5/12, like that. Okay, so I promise that that's going to happen on the next test, where I'm going to want you to show me that you know when to add, multiply, or subtract exponents like that. So you're going to have 3 things, 3 problems that are similar that are going to be kind of right next to each other like that. All right.
If we leave it as the negative, would it be considered wrong?
To simplify an expression with a negative exponent, I'm going to want you to write it with a positive exponent. Yeah. So it, you know, on a problem like that, Michelle, let's say that was a 4-point problem. I might take off a point. I might take off a half a point for doing something like that. But I would penalize you a little bit for not getting rid of the negative exponent. So you'd get most of the points, but you would get penalized a little bit for it. So. So moral to the story, get rid of negative exponents at the end on a problem like that. All right, so let's see. We've got a couple of different kinds of situations here. So let's say that we need to talk about before we say we're done. So let's say we have 16 x to the 4th power, and that's all raised to the 3/4 power. All right, so we're going to look at a little bit more complicated expressions that have fractions as exponents somewhere in there. Now, you don't do anything different on this problem than you would have if that 3/4 had been something that was not a fraction. So you're going to raise each of these factors separately to the 3/4 power. Like that. All right, now the 16 to the 3/4, let's do that one first. So what root am I talking about there? That's 16 to the 3/4. What's the root there? Remember remember that it is power over root. So what's the root? Whoa, be nice if I wrote it right. So what's the root? It's 4.
4.
Yeah, and then the power is 3. So the 4th root of 16 is 4th root of 16 is 2. Right? And so that would be 2 to the 3rd power, and then 2 to the 3rd power is 8. And so this is going to be 8 right here. 16 to the 3/4 power is the same thing as 8. And then x to the 4th to the 3/4, that's one of those where you multiply the exponents, right? Because you have a power, something raised to a power and then raised to a power again. And the 4's divide out, and you'll end up with 8x cubed as the final expression.
How did you get the 8?
That's what I was doing over here. Right? Remember that 16 to the 3/4, the denominator is the root. So you're talking about the 4th root of 16. 4th root of 16 is 2. Right? That 2 to the 4th power is 16.
So what do you do with the 3?
Well, look, I've got it written right there. What did I do? The 3 just comes down as the power, right? That's the power right there. So here's the 3. Here's the 3 right here.
Oh, I see. Okay.
Right. So what is 16 to the 3/4? What is the 3/4 power telling you to do? It's telling you to do two things. It's telling you to take the root, the 4th root of the number, and then it's telling you to take that and then raise it to the 3rd power. Right. So you had to do both of those things, and so that's what I did. We're going to look at another one like that. So okay. So let's say we have 25 x to the 8th, y to the 7th, and this is all to the 5/2 power. So we have another fractional exponent stuck in there somewhere. All right, so what is this? This is 25 to the 5/2. You're raising each factor individually to the 5/2. So this is x to the 8th to the 5/2, and then y to the 7th to the 5/2. All right, so let's do that 25 to the 5/2 kind of off to the side over here. 25 to the 5/2. What root am I talking about? Yeah, it's the second root. That's right. It's a square root. And then the power is 5. So what's the square root of 25?
5.
Yeah, it's 5. And then that would be raised to the 5th power. Right? So I took the square root of 25 first. That was 5. And now I'm going to take that and raise it to the 5th power. By the way, 5 to the 5th power is 3,125. Don't worry, I'm not going to give you anything that's going to be that big, but 5 to the 5th power is 3,125. And so you end up with 3,125 over here, and then x to the 8th to the 5 halves. And if you want to do all of those off to the side, that's fine. You can do that. So x to the 8th to the 5 halves is the same thing as x to the 8th times 5 halves, right? You multiply the exponents in that case. And so that would give you the 2 and the 8 would divide out and leave you the 4. So you have x to the 20th. And I think maybe somebody said that. Right, you get x to the 20th. And then finally the y to the 7th to the 5 halves. Y to the 7th to the 5 halves. You multiply again, 7 times 5 halves. By the way, nothing cancels out there, and so you'd just be left with y to the 35 halves. And you couldn't simplify that at all, so you just leave it alone like that. All right, we're kind of. Anybody have a question about that problem? Thank you, Jose. Anybody else have a question?
No.
And believe me, this is not trivial. My experience has been that students sometimes struggle with fractions as exponents, getting used to this. And so this is something that you just need to do some serious practicing on, and do lots of homework, lots of practice problems, kind of every day now going into exam 2, so that you can get ready for this stuff. All right, let's see. Let's look at a problem like this. X to the, let's say we have 20x to the 4/5 y to the 3rd over -2 x to the 1/5 y to the 2/3. Yuck. All right, so what I would do there is I would just kind of do that as 3 separate problems. And if you want to, you could do this off to the side. You have 20 over -2. That's just -10 over 1. All right. And so when you come back over to our problem over here, there's going to be a -10 and or a 10 and a -1. And you can put the negative sign wherever you want. Probably typically would be written in front of the fraction. Then you have x to the 4/5 over x to the 1/5. And you subtract those exponents, so you have x to the 4/5 minus 1/5. Don't need a common denominator there because you already have one. So that's x to the 3/5. And so coming back over to our problem, this would be x to the 3/5 right here.
Why would it go on top?
Remember, I'm just subtracting. You just get 4/5 minus 1/5. And what's the exponent? Is the exponent positive or negative? Exponent's positive, and so it's going to be on top. Now, the other way to look at that, Michelle, and this is just as easy to look at it this way, is where's the bigger exponent? Is the bigger exponent in the top or the bottom?
Okay.
Yeah, and you just put the x wherever the bigger exponent is. So, and then finally, you've got y to the 3rd over y to the 2/3. So you're going to subtract exponents there. So you have 3 minus 2/3. But that 3 is really 3 over 1. So this is, the least common denominator would be 3. So this would be 9/3 minus 2/3. And so you get y to the 7/3. And again, and Michelle, you asked about this on the x's, the bigger exponents in the top, so that y to the 7/3 goes in the top right here. And so the bottom has just got a 1 in it. And so this ends up giving you -10 x to the 3/5 y to the 7/3 at the end.
you put the negative 10 x to the 5th, y to the 7/3 at the bottom to make it positive, or no?
No. Remember, the only reason why you'd be moving anything is if the exponent was negative. This is just a negative number.
Oh, okay.
And so you just leave it sit.
Okay.
Yeah, you just leave it sit there. Remember, the only time you move things in a fraction is if you have a negative exponent. So.
Okay.
All right, so now we've covered a lot of material in the last hour and 20 minutes. So you've definitely got some things to practice here with higher order roots and radicals. More practice here. We covered sections 9.7 and 9.8 in the book. And so in section 9.7, this is on page 1104, I would look at anything from 443. I'm not going nuts with this section at all, though probably some of you think I'm going nuts with this anyway, but really just 443 through 463 odd would be okay there. And then on fractions as exponents, this is section 9.8. This is page 1123. And here I go 525 through, and you're not going to like this, but I would go through 597 odd. And some of those problems have 2 or 3 pieces to them also. So there's a lot of practice in there. But I can't tell you enough that going through and working some of those problems, even if you don't do all of those, if you do some of those, it's going to be good practice for the test. So this is good practice for exam 2. I was talking to somebody online last night who was there for my online office hours, had some questions, and what they were telling me was that that every night they were going through a different section in the book and doing problems as they're going into exam 2. And that's a really good strategy, is every day do, even if it's just 30 or 45 minutes, just working through some problems, keeping up with your WebAssign stuff, and doing that every day going into exam 2 is going to pay off in a big way. So now's the time to start really kind of getting prepped for that exam. So does anybody have anything last that they want to ask about before we shut this down?
No.
No.
I'm good.
Okay, then you guys have a great day. Remember my office hours this afternoon and tonight and tomorrow night. Come by for help. I'll be more than happy to help you out. Just for those of you who are listening live, and for those of you who are watching this video, Michelle, you're a good example. Michelle, you've come by my office in the evenings a couple of times, my online office in the evenings. Michelle, have I ever yelled at you or told you to not ask me questions?
No.
So I've always answered your questions, right?
Yeah, you might have told me that I shouldn't be asking it, but yeah.
No, come on, Michelle. I've never said that. So,
for the most part, yes.
Okay, so live testimony there that I'm not going to yell at you. That I want you to come by for help. So please do that. Have a great day. Enjoy the beautiful weather. Go outside in the sun and work algebra out in the sun. That would be awesome. So have a great day, and I will see you guys soon.
All right, bye. Thank you.
All right, bye-bye. Have a good day.
Thank you.
Have a great day.